Hi, everyone. I got a fun story to share with you all today. It is how the circumference of the Earth was first calculated. Cautionary tale, you might say. Okay, so Erastothenes, 276 BC, also known as a long time ago. He was the librarian at Alexandria. Now, this guy, he read a lot of books. He wasn't you know, strictly an astronomer or strictly a mathematician or strictly that sort of thing, but he was well versed in a lot of different fields, and he just read a lot of books. He was a librarian, right? So people gave him a hard time because he didn't pick one specific field and become like super good at it. And so they called him beta, as in like second rate scientist, whatever. So that's kind of an insult. A little bit ironic that all the people that were calling him that are gone and nobody knows who they are yet. This guy still goes down in history, and I'm talking about him today. So he was a Roman citizen uh, in of Greek descent in Egypt. So he had a lot of different dynamics going on there. And he read this book about a story from a place called Syene, which is also in Egypt. And in this story, there was a well in Syene where you could get water from. And on the solstice, summer solstice, you could see all the way down to the bottom of the well, which is really interesting to him because he says even on the summer solstice in Alexandria, there's a little bit of a shadow. So he goes, just an example here of the distance here between Alexandria out the Mediterranean Sea and Syene down here. It's modern day Aswan, I think. So he goes, I need to figure this one out because that's, that could be there could be some interesting results from that. He's not wrong. Because if there's a shadow over here and shadow over here and not over here, that means that like the Earth must be curved, which they actually thought it was even back then. That there was actually a curve to the Earth. I mean, you look up, you see the sun, you see the moon, that's round, that's round. They had some other interesting things, like when a ship sails, you see like the dip of the sail as it goes off in the distance. I mean, that's kind of an optical illusion, not really. A lot of that has to do with the curve of the Earth. But yeah, and I first came across this story when I was reading Copernicus' book for astronomy, just for funsies, and it was really interesting on the revolutions of heavenly spheres. You should pick it up because there's a lot of interesting asides. But anyway, basically, if there's no shadow here and there's a shadow there, that means that like one of them's tilted, one of them's not. So maybe you've got a curved Earth. So here's his thinking. You had Syene down here, and you had Alexandria here. And if you have the sun, I'll make the sun yellow. The sun, if it's far away, which it is, you're going to have all of the beams from the sun are going to be basically parallel at this point. So light coming in is going to be parallel at all points. Doesn't matter if you're in Alexandria or Syene, because it's so far away, a little bit of difference isn't going to be noticeable. Those are all parallel, even though that one's a little tilted. Don't worry about it. Okay, so I'm going to create a fun blue line here. You'll see why in a second. So we'll call this line coming in through Syene and going all the way to the middle of the Earth. Well, if you put it perpendicular to the Earth, it's a sphere. Anything perpendicular on a sphere will go to its center. This is an important principle. Okay, so now you also have on the solstice, Erastothenes went and he put a stick in the ground and he found, well, by golly, there's a shadow on the ground and that creates it was about 7 degrees. So, and he said 1/50th of a circle. They didn't use degrees, but 1/50th of a circle was the measurement that he got. That's not 70, that's 7. So make it look a little more 7-ish. That's less 7-ish. There we go. Okay, 7 degrees there. Okay, now check this out. And obviously that it just looks more than 7 degrees, but don't worry about it. This is enlarged to show texture. Okay, so I don't want blue, I want green. I'm gonna go away. We'll do green. All right, so here's what I'm gonna do. The stick that he put in the mud, because it's also perpendicular to the Earth, it will also go down to the very center of the Earth. All right, that makes sense? Okay. Now, those who have taken geometry might start to see what I'm setting up here. But the shadow that was left was because of a parallel line here. So I have 2 parallel lines with a transversal. Parallel lines are blue, the transversal is green. Now, there are certain rules, which if you're my student, you will know this, is that this angle and this angle are the same angle. If these two are parallel with the transversal, that means this is also 7 degrees. Okay. So this rule is called alternate interior. Yeah. They alternate and their interior angles, just like this one and that one are equal, that one and that one are equal. Okay. So he goes, all right, so this is 7 degrees or 1/50th of a circle. What about, I bet you if I was able to make a measurement and find out this distance, then since that's 1/50th, I could just multiply this distance by 50 and get the circumference of the Earth. Pretty smart. So basically, if he could find a way to measure from Alexandria to Syene, then he could figure out the circumference of the Earth. Problem is, it's 276 BC. Well, that's when he was born. So, yeah. Anyway, it's way back when, and they didn't have any great way of measurement. But what they did measure was a thing called stadia, which was steps. So basically, they measure out how many steps are from one place to another, and then they had a standard step width, and they had people that it was their job to be good at walking. So hopefully he paid somebody to walk from Alexandria to Syene, maybe on a camel, and give him that measurement, and then he would take that measurement, multiply it by 50, and he get the circumference of the Earth. Okay, so he did in fact do that. He found that this distance here was 5,000 stadia. I think stadia is like 1/8 of a mile. 5,000 stadia. Okay. Stadia, we'll call it S. Well, it looks like a 5. It's not, it's an S. Okay, so he goes, all right, so we've got 5,000 stadia. And we'll multiply it times 50. And that give him the right old number of 250,000 stadia. Now, stadia, although it was standardized, they had tables because, you know, there was some argument over how much exactly a stadia was. Depending on how tall you are, your pacing is going to be a little different. But they had standard stadia. So these figures are going to be, although the 5,000 and the 50 are normal, the 250,000 are normal. Okay, so what about, so stadia doesn't mean much to you and me anymore, but you can convert it to kilometers. That is a really bad K. There we go. Kilometers. Okay, kilometers, it's about, I'll do a little about thingy, 40,000 kilometers. Okay. Seems big. The Earth is big. Okay. How accurate was he according to today's geography? Well, the actual kilometers is 40,075. So not that bad. I mean, given that, you know, these numbers are going to be the conversion to kilometers is going to be rough. I mean, there could be, you know, a couple degrees, a couple percent error or whatever, but like it looks good. I mean, on paper it looks good. So yeah, let's look at this is what the internet. Yeah. So alternate interior angles are equal. Full shadow of the well sign near the Earth. Okay. All right. So why is this important? Well, obviously, you know, there's a lot of different things you can do with this information. But mostly humanity forgot it, because why not? So Ptolemy came around 100 AD or Common Era. He was known for modeling the Ptolemaic model of the solar system, which is probably why it was in Copernicus's book. But it was geocentric instead of heliocentric, meaning that the Earth was the center of the universe and the sun went around it and the moon went around it. He created a model, and it worked for like timing things, but it completely wrong. So astronomer, you know, okay. So cartography was his other thing that he did. So he created a really cool map of what they knew at 100 AD. So this is still Roman era, but like, I don't know, 350 years after Erastothenes. And it was pretty accepted that the world was curved then. It wasn't it was still somewhat controversial in some circles, just like even today we still have flat earthers. But so, you know, you can kind of see, okay, here's Europe, Africa. They hadn't been that far down, so they weren't really sure. And then, okay, yeah, India is getting a little weird. But all in all, it's fairly close, pretty good, accurate with the different people blowing the winds from all the different directions. So it looks pretty good. But if you looked at the actual Earth and compared it to this one, you notice it's a little small, a little smaller than the actual Earth is. And there's a reason for that, even though everything was measured out as precisely as you could, like with this compass measuring. Well, here's the problem. The estimate of the globe was smaller than it was because Ptolemy and Marinus, who helped him with the cartography on this one, adopted a calculation of 180,000 stadia. Remember, the actual number was 250,000 as the circumference of the Earth, using Poseidonius's calculations at 135 BC. And his calculations were based on like the angle of a star above the horizon, which can be problematic. Yeah, we'll just leave it there. But yeah, so basically he created this map is 27.6% smaller than the actual Earth is. No big deal. 180, whatever. People forgot after 350 years, or they actually, Poseidonius was actually 100 years after Erastothenes had already figured it out. But this guy did it wrong. So, I mean, he did it different and got a wrong answer. Eventually somebody's going to catch this, right? And be like, let's do another measurement of some other method or something. No. So 1420 AD or Common Era, Nicholas Germanus. So this is 1300 years after Ptolemy, and this is what's changed. This is why it's the Dark Ages, folks. Like, how do you go that long without updating your map? Like, oh boy. Anyway, and not only to that, but at no point in those 1300 years had anyone gone, hey, remember? Like, they still knew Erastothenes was a thing and had done his measurements, but they just were like, man, look, Ptolemy mapped it out. He's been right about everything else. Why not be right about it? You know, the Earth's the center of the universe. He's right about that. You know, okay. Now, what came of this? Well, if you notice, 1420 is when this dude was born. So this was the map, the very map that old Christopher Columbus used. He was born in 1451. Well, everybody knows about 1492, right? Okay, so he was able to market like, hey, I can, give me 3 ships, a couple hundred people, supplies, and I can make a trade route all the way to India because it's only 70,000 stadia, according to his incorrect calculations. So basically, if he had done the right calculations or just not used the map and maybe double checked things, then no one would have approved his mission, because if there wasn't the Americas, then everyone would have starved and no one would have ever heard of these folks again. He got lucky because there was something there. But basically, this is a cautionary tale. This is why you do your homework. Okay. This is why geometry is important. This is why math is important, is because when everybody pushes it to the side and worries about everything else, this is what happens. You'll go on an adventure, colonize places, and call people Indians. We still call people Indians today. So, yeah. Just as a final, sum this up, Christopher Columbus, although he'd had now evidence that, because somebody was like, yeah, that's not India, yo. He had evidence that he didn't actually make it to India. So his reasoning was, well, the northern hemisphere kind of comes in at the top, and he said it was like a nipple. So the northern hemisphere is like a nipple, and then it's more rounded towards the middle. So anyway, I thought this was a fun story. I wanted to share it with you. And yeah, Thanks for listening.